Good afternoon, everybody. Now we will have the third lecture by Markus Ahlers. So Markus, please start.
Yeah, welcome back. Let me share my screen with you. So last time we talked about cosmic ray transport. Today, my plan is to talk about cosmic ray sources, and I will start discussing cosmic ray sources in our galaxy and what sort of radiative processes are important to understand cosmic ray spectra on one hand, and also the emission of the sources of cosmic rays in terms of gamma rays and neutrinos. So we will start today, and this will then go until tomorrow. And as a reminder, I prepared one summary slide here. So this is a summary of the ingredients that I tried to derive with you yesterday and also on Monday. So we basically derived two forms of transport equations. We worked with the angular averaged phase-space density. So F here was the phase-space density, and phi was the monopole, the angular average. And using then an expansion in spherical harmonics, we could derive a transport equation, which is also called the angular average Boltzmann equation. And the terms that we derived are a convection term. So if there is bulk motion of cosmic rays, bulk motion of the medium with a velocity u, then we have the convection term. If there is a divergence of the convection, then we also have a momentum convection. So this is an adiabatic loss term from the compression of the fluid. And then we also derived a form of the spatial diffusion with a diffusion tensor that is denoted here as K. The term that we haven't talked about is another form of diffusion, that's momentum diffusion. So in our case, yesterday I talked about static turbulence. In general, if you have magneto-hydrodynamical simulations, these turbulence will be time dependent, and that means as cosmic rays are scattering with these magnetic turbulence, they can also transfer and receive momentum, and this leads to a diffusion in momentum space, which is a term that looks very similar to the spatial diffusion term, and K tilde here is one parameter that is the scale of momentum diffusion. And it turns out that this momentum diffusion term is actually related to spatial diffusion, but we will not have the time to go into the details here. Then, of course, cosmic rays can not only interact with magnetic fields, they can interact with gas, with radiation. So there are a couple of collision terms that we haven't talked about. These will become important later on when we talk about radiative processes. So these collisions will produce radiation and also neutrinos. And of course, on the right-hand side of this equation, we also need some sources of cosmic rays. So this is this term Q here on the right-hand side. So this equation here is completely equivalent to another form of equation that I list here. So the only thing that I did here is I converted the angular averaged phase-space density phi to the so-called spectral density. So spectral density means number of cosmic rays per volume and per energy, P0. So this is an expression which is parameterized in terms of derivatives of pi 0. And I've very briefly indicated in the last minutes yesterday how you convert this equation into this form. And there's actually one exercise that we already gave yesterday, but maybe now with this background, it's easier to appreciate. The solar potential exercise 3 from yesterday, that is basically trying to include these convection terms and compressive fluids in terms of the outflow of the sun. Okay, so today we would like to, I would like to talk about transport of cosmic rays in our galaxies from cosmic ray sources and what we can learn about cosmic ray sources. So we are in this sketch of the Milky Way at this position here. So this is the location of the sun. This is here the galactic center. And the typical diameter of our Milky Way, that is of the order of tenths of kiloparsec, so order 10 kiloparsec. Our distance to the galactic center is about 7 to 8 kiloparsecs. Not sure if you actually can see this. I'm trying to write red on blue. It doesn't seem to be that good. So I would like to discuss cosmic ray transport in our galaxy. And for that, I'm going to introduce a very typical model for cosmic ray physics, which is called the Leaky Box Model. So the Leaky Box Model is as follows. Let me try to bring up a blackboard. So in the Leaky Box Model, I'm going to approximate the galactic region of cosmic ray transport by a pill-shaped box. So the box is going to look like this. Hold on a second. Yeah, so this is my pill box. That's a very nice pill box. And so the galactic plane is contained here in this pill box. So this will be located here along the dashed line. And the size of the galactic plane, the location of cosmic ray sources, so the cosmic ray sources will be confined to a very flat region in this pill box. So this region here in the center where you have cosmic ray sources that has typically a vertical extension of the order of a few 0.1 kiloparsec. So this, in terms of the galactic scales, this is a very narrow region. Then the pillbox itself here, this is the region where we assume that cosmic ray can diffuse. And this region here has a size 2 times capital H. And this could be of the order of kiloparsec. So much larger than the confined region of cosmic ray sources. Now the galactic center is in the middle here of this pillbox, galactic center. And in the following, we will assume that the radius here is of the order of 50 kiloparsec. Yeah. So the total volume of this pillbox is then, of course, 2 times h times pi r squared. And if I'm using here for h of the order something like 5 kiloparsec, I get a volume that, so the radius is 50 kiloparsec, then the volume will be of the order of 7,000 cubic parsec. So this is our box. So this is not yet the leaky box, this is just the box. So why do we call this the leaky box? So we're now looking for cosmic rays which are contained in this box. And from the previous slide, we already know that we can approximate to first order the density of cosmic rays here by the contribution of sources and the diffusion in this pillbox shape. So in the simplest form, I can write down now an expression for the total number of cosmic rays. So the total number of cosmic rays is of course given by the integral over the volume. So this would be V. And I know that the time derivative of the cosmic rays is going to be equal to the gradient of so the diffusion term of cosmic rays. So inside this pillbox shaped Milky Way. And if I integrate here over volume, this is going to be the integral over the divergence of k times gradient of the cosmic ray sources. And then, of course, we also have here a contribution, a source term coming from the sources which are contained here in the middle of this pillbox. So this is here the cosmic ray sources, which are overall contributing over time with this Q tot term. So now we can use the divergence theorem. We can convert this expression here now to a surface integral ds times the diffusion tensor times the gradient of the cosmic ray density, n, spectral density, and again, plus the diffusion term here on the right-hand side. And so this expression here is basically now telling you that the total balance of cosmic rays in our galaxy is given by the total injection of cosmic ray sources. So this is a positive term. And then we have one term which is accounting for the diffusive loss of cosmic rays out the surface. So over time, cosmic rays will stream out of this box in arbitrary direction. And this is the reason why we call this a leaky box. So it's going to lose cosmic rays. So in the following, this term here is effectively a stream of cosmic rays through the surface of this pillbox shape. And we will approximate this in the following by an effective term. So this effective term is going to be minus the total number of cosmic rays in time divided by a lost time, which depends, of course, on the energy, which I denote here by P0, plus Q tot. So this is now another approximation of our Boltzmann equation. Now let me bring up another blackboard. Are there any questions so far?
I have one question.
Yeah, go ahead.
From the draft, it means the direction of the magnetic field is vertical of galaxy.
Good question. So here I'm not considering a regular magnetic field. It is true that if you look here at the sketch of the galaxy, then for example you see here spiral arm structure. So these arms here. So in general, you would expect that magnetic fields will also align with these spiral arm structure. But for our discussion, this will not be important. What we are going to assume in the following is that cosmic ray diffusion is isotropic, so there's no preferred direction which would be dominated by an external regular magnetic field.
Okay, thanks.
So, I mean, the geometry here is entirely given by the orientation of the galactic plane. This is at the moment not saying anything about local magnetic fields in this box. Okay, thanks. Yeah, of course, the blue lines here, they can also be emitted in an angle. So, so this is not following, I mean, this is not indicating like the gyro motion of cosmic rays along magnetic fields.
Also going back to the transport equation, I'm sorry.
Yeah, no, go ahead, Konstantinos.
Okay, yes. So going back to the transport equation,
yeah,
are we neglecting any terms like momentum convection?
That's right. So I'm not considering convection at the moment.
Okay.
And so this is actually a strong approximation because we know that there is outflow of our galaxy, simply coming from the fact that we have dying stars in our galaxy, which will create supernova, and the supernova will create a steady stream of plasma that goes out of the galaxy. So for this approximation, I neglect these convection terms.
Okay, thank you.
There was another question by
Yeah, I was actually going to ask the same thing, so thanks.
Okay. Yes, okay, so I'm really only going to focus on these two terms here, this, and three terms with the sources, neglecting anything else. And we will see that we can get surprisingly far by this very simple approximation. So in the following, we would like to look at the steady state solution. And the steady state solution for the total number of cosmic rays in our box is, of course, just this equation here. So that means I can now make a relation between the cosmic rays contained in the box. So the solution now becomes the number of cosmic rays is going to be those produced by the sources. And so this is not, so this is Q tot P0. So this is an energy dependent total average spectrum times the lost time. Now, the lost time is going to be a diffusive lost time. And we have already talked last time that the diffusion tensor is going to have a rigidity dependence depending on the turbulence of the turbulent magnetic field, depending on the power spectrum of the turbulent magnetic field. So the lost time will depend on P0 via the rigidity dependence. And that means that the lost time should scale as P0 to the power minus delta. And delta was the rigidity dependence index coming from the diffusion tensor. In the case of Kolmogorov spectra, we estimated that delta should be of the order of 1/3. So this would be Kolmogorov. But there are also other types of turbulence. For example, delta could be closer to 1/2 in the case of Kraichnan turbulence, which is it's a different power law dependence on turbulence. So, so this is going to be the energy dependence of the lost term. And then, of course, the spectrum which is emitted by the sources, that will also have a spectral form. And later on, when we talk about Fermi acceleration, this also goes back to the first exercise of yesterday. We assume that this is another power law dependence. And so this goes like P0 to the power minus gamma. So gamma is the spectral index emitted from the source. So that means the entire cosmic ray population that we observe should scale like, so the spectrum should scale like P0 to the power minus gamma plus delta. So we are not expecting to see locally the cosmic ray energy distribution that is emitted or generated in the sources. Instead, we will see something that is softer. So it has a larger power law index. So in the sources, if we are looking here for Q, P0 and P0, and this is here a logarithmic scale, which is difficult to indicate here on the blackboard. So in the sources, we assume that the spectrum goes like P0 to the power minus gamma. But then due to cosmic ray diffusion, this power law spectrum is going to become softer. So this is P0 to the power minus gamma plus delta. And what this basically tells you is high energy cosmic rays have it much easier to escape from our galaxy. So they are diffusing out faster, whereas cosmic rays at lower energy, meaning lower rigidity, will be contained in our leaky box for a longer time. And basically this effect of containment and loss will steepen the spectrum according to the rigidity dependence of the diffusion tensor. And in the very first lecture, I already introduced cosmic ray spectra. I told you that for low energy cosmic rays, the spectrum that we observe locally is very soft. So the locally observed cosmic ray spectrum goes like P0 to the power minus 2.7. And if we now account for the fact that we have a rigidity dependence of the loss term, and let's say we have something like Kreisheim turbulence, which would give you delta equal 1/2, then the cosmic ray spectrum should be closer to P0 to the power minus 2.2. So the emission should be close to e to the power minus 2. And this is again consistent with our rough expectation from Fermi acceleration. Remember the exercise 1 that we had yesterday. Oh, yeah. Actually, I had prepared the slide here, so I didn't have to draw it. So what I'm talking about here is the cosmic ray spectrum at lower energies. This is here what is called F here is basically the density. And this is multiplied by e to the power 2.6. And this is flat here at the beginning. So it's about e to the power 2.6, 2.7 at low energies. And we have already talked about the size of the Lama radius in the previous lecture. So the Lama radius, to remind you, was given by 1.1 parsec for cosmic rays with a rigidity of 1 petavolt and a magnetic field of the order of 1 microgauss to the power minus 1. So was there a question? Okay. So so 1 petavolt for protons means an energy of 1 peta-electron volt. So this is on this axis here at 10 to the power 15 electron volt. Microgauss is the typical magnetic field strength, also of the turbulence in our leaky box. So that means the Lama radius of these cosmic rays should be of the order of 1 parsec. So 1 parsec is smaller than the vertical extension of our leaky box, which was of the order of 100 parsec. But you can see if we go now up in rigidity, let's say to 10 to the power 17, then we are reaching a Lama radius which is of the order of 100 parsec. So for that reason, we don't believe that the cosmic ray spectrum that we see locally at Earth can be dominated by galactic sources in this energy region. So cosmic rays at these energies can freely escape our leaky box, our Milky Way, and will be then maybe observed by extraterrestrial civilization somewhere else. But galactic sources can only dominate up to energies of a few 10 of peta-electron volt. For that reason, we believe that the lower energy end of the cosmic ray spectrum, basically up to the knee, this feature that I introduced earlier. So this should be dominated by galactic cosmic rays, whereas very energetic cosmic ray sources should originate in extragalactic sources. It is still a matter of debate where actually the transition between galactic and extragalactic cosmic ray sources occur. So there are some interesting intermediate features like the second knee, which is an additional softening of the spectra, which could maybe indicate the maximal energy of iron acceleration in sources, because iron has a higher charge. Or it could be like an intermediate population of sources, which could be either galactic or extragalactic. Are there any questions?
I have one question. I mean,
Yeah.
for the cosmic ray with the energy 10 to 17, yeah, the Lama radius is 100 parsec, and it's much smaller than the size of the box, right? But
yes,
but you said for this energy of cosmic rays, you just said it can go outside the galaxy very easily. Why?
So you're absolutely right. When I was talking about the extent of the Milky Way, I was using here a radius of 15 kiloparsec. That is much smaller. But the vertical extension, the vertical extension here is also of the order of 5 kiloparsec. Yeah. So you're right. This argument does not quite go through as I intended. Yeah. So of course, this is only like this is an approximation, assuming that the diffusion, for example, the strength of the magnetic field is completely constant over a very wide distance scale of 5 kiloparsec. In reality, we would expect that there's also a vertical dependence on the diffusion coefficient. And so as you go out, as cosmic rays are streaming out, they will see then weaker turbulence. And for those cosmic rays, it's then easier to escape. Okay. Yes, you're right. It's a good point. So it does not quite go through with the pillbox shape that I was drawing there.
Okay.
My apologies. Yeah.
Thanks.
Okay. Then at least from this very simple model, we understand why the spectrum is rather soft, because there are also diffusive aspects that we have to take into account. Now, we of course don't know what the loss time is. So the loss time was an effective parameter that we introduced. But we can actually measure the loss time, or at least the rigidity dependence of the loss time, by looking for the ratio of secondary to primary cosmic rays. So for that, I'm going to write down another differential equation, and this differential equation is going to parameterize the total number of secondary cosmic rays in our Milky Way. So the S here means secondary. So secondary here means that these are particles which are not emitted from cosmic ray sources predominantly, but instead they are produced by cosmic ray interactions in our galaxy. And the interaction which is important here is a so-called spallation process. You have very heavy energetic cosmic rays which are scattering with gas in our galaxy. And in this process, they will create, via spallation, nuclei with a lower atomic mass number. So this is a way to create secondary cosmic rays. And for these cosmic rays, because they are diffusing, you also have a loss term. So this is basically the same loss term that we introduced before. But then the source term will here be replaced by an effective source term that depends on the interaction with primary particles, so particles which are actually emitted in cosmic ray sources. So, and these interaction terms can be parameterized in terms of the velocity. So here I'm going to assume relativistic particles. So the velocity will be equal to the speed of light. And so in natural units, this is equal to 1. So the interaction will scale with the density of gas in our galaxy and the cross-section of spallation that transfers primary to secondary cosmic rays. And this multiplies the total number of primary species in our galaxy. So the P here does not mean momentum, it means primary. And of course, the primary cosmic rays, they will be dominated by the production in sources, but of course, they will also be lost from our galaxy. So we have these two differential equations. Now, if we are looking for the steady state again, we can solve this coupled set of differential equation very easily. And the solution can be expressed in the following way. The number of secondary cosmic rays divided by the number of primary cosmic rays is simply given by the loss term that we introduced earlier times the effective interaction rate, which is simply the density of the gas and the cross section for primary going to secondary particles. And so it turns out that the cross section that for spallation that I introduced here, that actually has a very weak energy dependence. So for simplicity, I will assume that this is a constant. And of course, also the gas density does not depend on the energy. So this expression should actually then scale as by the rigidity dependence or the energy dependence of the lost time itself. So this again should scale like P0 to the power minus delta, because this here is roughly constant in terms of energy. And so by looking now for secondary to primary ratios, we can actually measure the rigidity dependence of the loss term. And this is, for example, done with the boron to carbon ratio. And on Monday, I was talking about chemical composition of cosmic rays. And we observed that for lithium, beryllium, and boron, the abundance is much higher than the abundance of that we observe in our solar system. So that is an indication that lithium, beryllium, and boron are actually dominated by secondary production in cosmic rays. So we do not have to worry about primary acceleration of boron. So if you're looking for boron to carbon, and so boron is produced by spallation processes of carbon, we can use the ratio to infer the energy dependence of the loss term. And it turns out that here in the intermediate region between 1 gigaelectron volt to 100 gigaelectron volt, this boron to carbon ratio agrees quite well with a Kolmogorov type spectrum, where the dependence goes like e to the power minus 1/3. Sorry, this should be minus 1/3 and not 1/3. So this is one way to use the leaky box model to infer the lost time dependence. And for the measurement of the absolute time scale of cosmic ray loss, we can look for the abundance of, so the relative abundance of radioactive, so decaying cosmic rays, so-called cosmic ray clocks. So once you produce a secondary cosmic ray in spallation processes, if this is not a stable particle, it will eventually decay. And if you now look at the population of particles and look for the relative abundance, you can use the observed or the measured lifetime of these particles to say something about the containment in the galaxy. And for that, it is useful. So we're looking for the relative abundance of radioactive isotopes. And here again, I have an expression for secondary cosmic rays. Here again, we will focus on beryllium. Beryllium was one of these three elements that was dominated by secondary production. And it turns out that the beryllium isotope, beryllium-10, is unstable. It has a lifetime of tau equal to 1.5 million years, 10 to the power 6 years. So now if I'm looking for the differential equation for beryllium-10, so let me write this as N10 for beryllium-10. Then this will not only have a loss term coming from the diffusion out of our leaky box, but now I also have here a decay term. Sorry, this is not S. I wanted to call this, so this is here 10. And now it will also have a decay that is, of course, depending also on the energy of the particle. So the decay of the decay of 1.5 million years is, of course, in the rest for the beryllium at rest. So for cosmic rays with a certain velocity, the decay again will depend on energy, same as the loss. And then we have this effective production term with primary particles that are undergoing spallation. So this will be the differential equation of the primary. Now, I can solve this for the steady state, and the solution in steady state is given as n, sorry, keep changing my notation, so n10 P0 is given by gas density spallation cross-section. And now I have two terms here, the loss term from the galaxy plus the decay term times the primary abundance. So this is for the case of the long-lived, but nevertheless radioactive beryllium-10. I can do the same exercise now for other isotopes of beryllium. And here in particular, we have to look for the stable, isotopes beryllium-7 and beryllium-9. So beryllium-9 is absolutely stable. Beryllium-7 is actually not stable. I mean, in atomic form, it has a lifetime of the order of a few tens of days. But here we are talking about completely ionized particles, so the nuclei. And beryllium-7 is decaying by electron capture. So, but if there is no electron around in completely ionized beryllium-7 nuclei, then this is effectively stable. So in terms of cosmic rays, beryllium-7 is stable. So I can now repeat the exercise for beryllium-7 and beryllium-9. It's basically the same differential equation except for the decay term that I introduced for beryllium-10. And so the final expression in steady state of beryllium-7 and beryllium-9 will look the same without the decay term that I introduced here. Now, if I look now at both steady state solution, and I can combine this, and I can write this as the ratio of beryllium-10 divided by the ratio of beryllium-7 and 9. And this will depend on the inverse loss time, depending on energy, divided by the loss time plus the decay time of beryllium-10. And then here on the right-hand side, I also have the ratio of spallation cross-section. So this will be primary going to beryllium-10 divided by primary going to beryllium-7, and so the partial cross-section going to 7 and that one going to 9. So the quantities that you have here on the right-hand side, these are basically determined by particle physics measurements. So you go to the lab and you measure the spallation cross-section of primary cosmic rays. And the terms here on the left-hand side, they can be measured by the relative abundance of these elements, for example, by the AMS detector that is very sensitive to individual isotopes. And by then comparing the measurement together with the ratio of the cross-section, we can actually infer the loss time, the effective loss time at a given energy of cosmic rays. So it turns out, including all these measurements, we arrive at an observed lost time at an energy of the order of 100 mega electron volts. So this is at the lower end of the cosmic ray spectrum of T loss of about 15 mega years. So 50 million years. This is about the time scale that a 100 mega electron volt cosmic ray will on average escape via diffusion from our galaxy. Okay, so finally, equipped with all these ingredients, we can now try to estimate what is actually the required power of cosmic ray sources in our galaxy that the observed cosmic ray spectrum, together with the loss of cosmic rays from our leaky box, is consistent with the total power that is provided by these sources. So we can now look for the energy density of locally observed cosmic rays. So the energy density is denoted here by omega cosmic ray. And this will be the integral over the energy weighted by the energy. And then you have the spectral energy distribution. So this quantity is, from our measurement, roughly 1 electron volt per cubic centimeter. Now, the total energy of cosmic rays is now given by the local density. And if we assume that the local density is a good representation for the cosmic ray density at other places in our leaky box, I can simply multiply this by the volume of our leaky box to get the total energy that is contained in cosmic rays at any given time. And then the luminosity or the power of all cosmic ray sources in our galaxy will be simply given by volume times cosmic ray density over the lost time. So this is also the reason why I choose here cosmic rays at an energy of about 100 mega electron volt, 100 mega electron volt, because this is basically the peak of the steeply falling cosmic ray spectrum. So most of the energy density is sitting at low energy cosmic rays. So using this approximation of our pill box with an extent of about 10 kiloparsec in the vertical direction, I can then come up with an energy or total luminosity of the sources, which is roughly 5 times 10 to the power 53 electron volt per second. And this can also be expressed in terms of ergs, 7 times 10 to the power 41 erg per second. So erg was defined as 10 to the power minus 7 joule. And so you can convert between electron volts and ergs in our natural units. So this is an estimate of the total power of cosmic rays. And it was actually speculated by Bade and Zwicky already in the 30s, that maybe the total population of dying stars in our galaxy, which are forming supernova and supernova remnants later on, could be responsible for the generation of cosmic rays. So for supernova remnants, so dying stars, we have a rate in our galaxy, a rate rate R, which is about 1 supernova per 30 years. So per century, we expect to see 3 core collapse supernova in our galaxy. So in a core collapse supernova, the kinetic energy of the ejecta, kinetic energy of ejecta. That is about 3 times 10 to the power 51 ergs. And actually later today, or maybe early tomorrow, we will actually derive this quantity from general energetics considerations of the core collapse of a massive star. So if you are using these 2 ingredients of the kinetic energy and the rate of these supernova remnants, we see that the supernova remnants or supernova can provide about 7 times 10 to the power 41 ergs per second if a fraction of about 20% is converted, so 20% of the kinetic energy of ejecta of supernova remnants is converted to the acceleration of cosmic rays. So 20% is a fairly large value. It means a process, we have to consider a process of cosmic ray acceleration that is very efficient. And we will talk about efficient cosmic ray acceleration later on when we talk about diffusive shock acceleration or first order Fermi acceleration. So that's basically the last point I want to say about the leaky box model. So the leaky box model allows, it's a simplified model, and you're right, you already had some questions that it omits a lot of things, for example, convection. It might also not work perfectly when you look for the containment in this leaky box when you look at the spectrum. So there is some uncertainty. But what you can learn is one thing: cosmic ray spectra are softened by energy-dependent diffusion, and this is consistent with the observation. We can estimate that cosmic rays at low energies of the order of 100 mega-electron-volt remain about 15 million years in the galaxy. And supernova remnant could be a good source of cosmic rays if we manage to find actually an acceleration mechanism. Okay, are there any questions at this point?
Yes, I have a question.
Yeah.
So previously you mentioned that the spallation cross-section is energy independent.
Independent.
Independent, yes.
Independent.
So what is a typical value of it? And so regarding the various isotopes, which is the dominant?
So you are talking about this expression here, the relative contribution?
Yes.
This is something I don't know by heart. So this is something that can be measured in lab experiments. And so you basically take here the relative contribution of spallation. Of course, there is also some dependence here on the initial primary. So you have to, so this argument here is a little oversimplified. In principle, you have several primaries that can produce this beryllium 9 via spallation. And so if you really want to arrive at 50 mega years, you have to take into account the full interaction chain of cosmic rays in our galaxy.
I see. So only through observations we have the data. There's no parameterization of this cross-section.
Yes. So I mean, you can of course also consider here the weak energy dependence of the spallation cross-section. So if I mean all this goes into a more and more precise estimate of this lost time scale. What you have here on the left-hand side is the cosmic ray observation. So this is astrophysics. On the right-hand side, you have the particle physics observation from the lab. And comparing these two quantities to each other allow you to say something about the lost time. The decay, of course, is also something that you can measure in the lab. But you can see that from this, you can infer the lost time from this equation. Okay.
Thank you. Yes.
Okay. Then, okay, we found now a suspect for cosmic ray acceleration, which is supernova remnants. And if we are looking for cosmic ray accelerators, we basically have to consider two important aspects, similar to what happens with earthbound accelerators of particles. So you want to accelerate particles in astrophysical environments. And on Monday, I already said that we often encounter plasma environments, and plasmas do not support electric fields over a long time. Whenever you have an electric field which is built up in a plasma, this is immediately short-circuited by motion of particles. So if you are trying to look for an analogy of acceleration in terms of collider experiments on Earth, for example, here the Large Hadron Collider. So this is here Geneva, and this is the outline of the Large Hadron Collider. You can consider acceleration of cosmic rays in electric fields. So cosmic rays have to be stored via a collider ring. So particles are kept in circular motion via magnetic fields, magnetic dipole fields. And while they are confined in these magnetic fields in your storage ring, they are continuously accelerated by electric fields. So there are two parts of the problem, the confinement and the acceleration. So the Hiller's criterion is basically giving you the necessary condition for cosmic ray confinement in sources. And the argument is very similar to that of accelerators. So we have already introduced the Lama radius. The Lama radius in our galactic units was 1.1 parsec. And then energy over peta electron volt and galactic field over micro Gauss. Now, if I can convert this equation into a condition on the maximum energy that can be reached by an accelerator with a characteristic size and a characteristic magnetic field. So I can write this expression as the following. So E, so the maximum energy a particle can reach in my astrophysical environment or in my particle collider, my storage ring, is given by 0.9 times charge. So here's actually also a charge factor in the Lama radius. And then I have here a radius in units of parsec, and the magnetic fields in units of micro Gauss. And this energy has units of peta electron volt. This is, of course, a simple rewrite of the Lama radius equation. So if I have an environment, an astrophysical source, which has a typical size R, I can confine cosmic rays via regular, but also with irregular, by turbulent magnetic fields, diffusively in my environment. And as long as I find an acceleration mechanism, I can confine these particles as long as the energy is smaller than this expression here. So this will be the maximum energy. Once particles have reached the energy, the Lama radius will be so large that they can easily escape out of this environment. So this is called the Hiller's criterion. You can also use the same equation here to look how this Hiller's criterion would look like for the LHC, so the Large Hadron Collider. So for the Large Hadron Collider, we have a radius of the storage ring, which is of about 4 kilometers. And the dipole magnets that are keeping protons in the storage ring have a magnetic field which is of the order of 8 Tesla. And if you plug these numbers into your Hiller's criterion, you end up with a maximum energy at the LHC that should be 9 tera electron volt for 4 kilometers and 8 Tesla. Yeah, and this is roughly the right energy that you can achieve with the individual beams before they are brought to collision. So the center of mass energy in these collisions is of the order of 14 tera electron volt. Okay, so this is basically a direct analogy between acceleration of particles in earthbound accelerators and those in astrophysical environments. Now, this Hiller's criterion, so this very simple equation is basically the geometric condition of the Hiller's criterion. However, you can imagine that in astrophysical sources, it is not only the storage of cosmic rays. There are also other effects that leads to the emission of cosmic rays. So you could also have diffusive processes that are stronger and lead to a leakage of cosmic rays, or you could have collisions of cosmic rays that allows them to which prevent cosmic ray acceleration to a very high energies. So if we are simply taking this geometric condition and try to look for the maximum energy for supernova remnants, so in supernova remnants, if I assume that I have magnetic fields of the order of micro-Gauss, so similar to the magnetic fields that we find throughout our galaxy, and if I'm also considering very extended supernova remnants after about 100 years, so after 100 years, they will reach a size of the order of 1 parsec, then the maximum energy of supernova remnants should be of the order of peta-electron volt. This is basically exactly the expression that we had here. So micro-Gauss magnetic field in supernova remnant and a size of the order of 1 parsec gives you 1 peta-electron volt. So this is actually, again, very interesting because if we are going back to the cosmic ray spectrum, here is 1 peta-electron volt. So the feature that we see here, the Ni, that could be actually an indication that supernova remnants are running out of steam. And so the power law spectrum will come to an end, will have an exponential cutoff. And this exponential cutoff might then have a rigidity scaling for different types of nuclei. And the superposition of these spectra will then introduce this softening of the spectrum that we see beyond the Ni. However, it turns out that if you do the full argument, so in supernova remnants, the maximum energy, I should finish this sentence here, E max should be of the order of 1 peta-electron volt, just for geometric conditions. But it has been argued that this is a very optimistic maximum energy. There are other conditions that are at play here. And what's also important in supernova remnants is the velocity of shocks, because as we will learn later on, shocks and diffusive acceleration in shocks are the candidate mechanism for cosmic ray acceleration. And so the scaling that is usually assumed is slightly modified compared to this simple geometric argument. So here again is the formula for maximum energy. And you recognize you have here the size of the accelerator and the magnetic field of the accelerator. But here you also have 1 extra term, which is beta shock. And this is the velocity of shocks in supernova remnants relative to the speed of light. Typically, these shocks are very fast. So they reach of the order of 1% of the speed of light. but this factor here diminishes the total energy that you can reach in supernova remnants by a factor 100. So instead of peta-electron volt, we would reach an energy of the order of 10 tera-electron volt. So much, much lower than the need that we see in cosmic rays. However, it was also argued that there could be additional effects in cosmic ray acceleration, and which will enhance the maximum energy that you can reach in supernova remnants. And we will come back to this when we are talking about diffusive shock acceleration. Here is a summary of different astrophysical sources that you can imagine, galactic sources as well as extragalactic sources, neutron stars and very magnetic neutron stars, so-called magnetars, are very compact sources with high magnetic fields, but you could also have very extended sources here in the upper end of the spectrum with low magnetic fields, active galactic nuclei, lobes, which are produced by jetted outflows of active galaxies. So these are basically, this plot here shows the magnetic field strength over the size of the accelerator. And you can see that there are a couple of candidate sources that can actually accelerate cosmic rays to very large energies. The lines that you see here, so there are 4 types of lines. The blue ones are indicating the combination of magnetic field strength and size that allows to accelerate iron up to 10 to the power 20 electron volts. And the solid line here is for very efficient shocks which are close to the speed of light, beta is equal to 1. The dashed lines are for the case where you have, like supernova remnants, only a fraction of the velocity of the speed of light. And the red lines here are proton. Because protons have a lower charge, you would need larger magnetic fields or larger sized objects to accelerate particles to this point. What you see here in brown is supernova remnants. So supernova remnants are not expected to accelerate cosmic rays all the way up to 10 to the power 20 electron volts. So this plot here is mainly focusing on the sources of ultra high energy cosmic rays. But you can see that you come very close to these lines, indicating that it is possible to accelerate cosmic rays to these energies of the order of peta-electron volt, as we did on the previous slide. Okay, I think this is a good time for a break or for some questions from your side.
I have one question.
Yep.
For the supernova, it can accelerate the cosmic ray up to 1 PeV, right? But what about the even higher energy? How to accelerate?
Yeah, good point. For the upper end of the cosmic ray spectrum that you see here, we need to find extragalactic source environment. So it's not possible to confine cosmic rays in the galaxy at these extreme energies. So if there was a cosmic ray source that would accelerate cosmic rays up to these energies, it would appear actually as a very bright cosmic ray source. And we would have found this in cosmic ray experiments. So necessarily these sources have to be of extragalactic origin. And there are various types of sources that have been speculated. For example, gamma ray bursts, which are formed by also by the death of supermassive stars. They can produce jetted outflows that produce shocks via internal collision. And these shock environments are again environments where cosmic ray acceleration can take place. In general, you have to find a source which is not only able to confine cosmic rays, but it also has sufficiently weak magnetic fields, for example, that you are not losing energy via synchrotron emission. So gamma ray bursts could be one example. Also active galactic nuclei, in particular blazars with jetted outflow, can also be responsible for ultra high energy cosmic rays. I talked about this Auger experiment on Monday. Auger has also done an analysis of the arrival direction of very energetic cosmic rays. I think I will have some time on Friday to talk about this. And what they find is that the arrival direction shows some evidence that the cosmic rays are coming from the direction of starburst galaxies. So that's very interesting. So starburst galaxies are another environment where you have a high potential for gamma ray bursts, because starburst galaxies have an increased star formation rate, and correspondingly, you will also have a higher chance to produce gamma ray bursts. So this might also support this idea that gamma ray bursts are responsible for these energetic cosmic rays.
Okay, but the basic principle is the same from the Fermi acceleration, right?
Yes. Yes.
Okay.
Yes. I mean, at least as if you are trying to look for standard astrophysical sources, it has also been speculated that maybe there is some exotic origin of very energetic cosmic rays. Maybe you could have some topological defects, which are remnants from the early universe, which are decaying. And these decays of topological defects could also lead to very energetic cosmic rays. So this would be another exotic possibility, but for astrophysical acceleration, we will have to look for Fermi acceleration.
Okay, thanks.
Yeah, I should maybe mention that, so I said that electric fields are not supported by plasma. You can have certain situations where you can also have acceleration by electric fields. For example, you can look for magnetic reconnection. Solar flares are actually events where magnetic reconnection takes place, and these solar flares can produce energetic particles that are accelerated by the electric fields which are formed by magnetic reconnection. So this is actually an example for an alternative mechanism. However, solar flares are not responsible for ultra-energy cosmic rays. I mean, they are actually dominating cosmic rays at much, or contributing to cosmic rays at much lower energies. Another possibility would be if you have a neutron star, which with a very strong magnetic field. And if this neutron star is rotating and the axis of the magnetic dipole is not aligned with the axis of rotation, you will have a time-dependent rotating dipole. And a time-dependent magnetic dipole will also cause radiation. And so basically you will create a potential drop via the rotation of neutron stars that can also lead to particle acceleration. And so this is another mechanism, but again, it's not possible to really reach these ultra high energy cosmic rays by in this way.
Okay, thanks.
Yeah, so maybe one comment. So on Monday, I also gave you a list of references. There were also some references that are particularly focusing on ultra energy cosmic rays. If you're interested in this subject, it's also worth taking a look at that.
Okay, thanks.
I just wanted to ask if it is possible to have a cosmic ray emission from a neutron star merger.
Yes, a neutron star merger, that's actually a super hot topic. Neutron star mergers are actually one of the sources of short gamma ray bursts. And I will have some time on Friday to talk about this. These neutron star mergers can be sources of gamma ray bursts. And as I said, gamma ray bursts are sources also for cosmic rays. Neutron stars, so this is after all a lecture on multi-messenger astronomy. The source that you mentioned, binary neutron star mergers, are probably the most interesting multi-messenger sources. You can observe them in terms of gravitational waves just before the merger in the in-spiral. And then if you form a short gamma ray burst, you can see these short gamma ray bursts in terms of photons, gamma rays. And there's also a chance that you accelerate cosmic rays, and these cosmic rays could interact and produce neutrinos. So these sources could be observed simultaneously in gravitational wave, gamma rays, and neutrinos. We have, in 2017, we have seen such a source in terms of gravitational waves and photons. And, I'm a member of a big collaboration, the ICE collaboration, who's looking for neutrinos. We also tried to see neutrinos from this object, but we couldn't find anything. If we had found neutrinos, this would have been a conclusive proof that gamma rays are sources of cosmic rays. This I'm going to talk about tomorrow.
Okay, thank you.
Okay. Let me have a sip of water. So let's continue then. So the Hiller's criterion that I show here is a necessary condition for confinement, but it's of course not saying anything about the acceleration mechanism. So in our particle collider at the LHC, we have a storage ring, and the storage ring is confining particles, but we have to find acceleration units. So what are the acceleration units that we can consider for astrophysical sources? And so I already mentioned diffusive shock acceleration several times. This is a type of Fermi acceleration. It is a mechanism that was proposed by Enrico Fermi in the 40s. So he wrote a paper on the origin of cosmic radiation. And he mentioned here in this paper that he is considering the case that the main process of acceleration is due to the interaction of cosmic particles with wandering magnetic fields. And so the picture that he had in mind is the following. You have magnetic clouds, and you have an environment where these magnetic, so it's basically a pocket of plasma that has turbulent magnetic fields. And these pockets of plasma, these clouds, are moving through the Milky Way, and cosmic rays are interacting with these clouds. So what I'm indicating here in this plot is a cloud. A cosmic ray particle is entering this cloud with an initial form momentum P1. And after this cosmic ray has entered the cloud, which is moving in this direction here, so the arrow here is the velocity of the cloud. So once it has entered this cloud, it will start to interact with magnetic turbulence in the cloud. And this is, of course, the process of diffusion that we introduced on Tuesday. So, and then after some scattering in magnetic irregularities, in magnetic turbulence, the cosmic ray will eventually be emitted from this environment. So we can look at this scattering process, and this is, of course, in this picture happening at many places, at many times in the Milky Way, at least as Fermi originally had this acceleration process in mind. So in the following, we are going to look at the energy balance of cosmic rays entering and exiting the source, and what this predicts for the average acceleration process. So as I said, initially a cosmic ray will enter the cloud with a form momentum P1. So P1 has here an energy component E1 and a three momentum P1. And so now this cosmic ray is entering the moving magnetic cloud. And I can now go to the reference system of the cloud. So after so particle 1 enters cloud, which is moving with a velocity beta and a relative angle theta 1. I can now look for the energy in the reference system of the cloud. So E1 prime is now the cloud's reference system, and this is now related to the initial 4-vector by a Lorentz transformation. So this will be gamma times E1, 1 minus beta cosine theta 1. So E1 and theta 1, these are the initial energy and the scattering angle of the particle with the cloud. So after the cosmic ray has entered the cloud, magnetic turbulence will isotropize the velocity of the particle in the cloud. So that means that when the particle eventually exits the cloud, so on exit of cloud, the particle in the reference system of the Milky Way is going to have a new energy, E2, which is given by gamma times E2 prime, 1 plus beta cosine theta 2 prime. So theta 2 prime is going to be the relative emission angle from the reference system of the cloud. And this is here plus sign. So now the question is, what is the relation here between E1? So this was the energy of the cosmic ray on entering the cloud, and E2 prime is on exit. Well, if the particle is only scattering collisionlessly with magnetic turbulence, E1 prime and E2 prime is going to be identical. So there's not going to be any acceleration happening in static magnetic fields. So the magnetic fields will simply have isotropized the emission direction. So isotropization, sorry, my handwriting is degrading again. Isotropization, I hope this is an English word, will basically randomize the velocity, but E2 prime is going to be equal to E1 prime. So now I can look for the total energy change from this one scattering process, cosmic ray entering the cloud and again exiting the cloud. So the energy budget is given as delta E over E1. And delta E is defined as E2 minus E1 divided by E1. And using the previous equations, I can write this as gamma squared 1 plus beta cosine theta 2 prime times 1 minus beta cosine theta 1 minus 1. So this is going to be the energy gain, depending, of course, on the relative scattering and emission angles. Now, because the clouds are moving at random direction in the Milky Way, I can write down the approximate collision rate of cosmic rays with these randomly oriented moving magnetic clouds. So the collision rate of cosmic rays entering the cloud, collision rate on enter, is proportional. So it will depend on the angle, and it's proportional to 1/2 minus beta cosinus theta 1. Yeah, so this is basically, so what you see here is the relative velocity between the entering cosmic rays, so the relative velocity of cosmic rays entering in this direction, and the velocity of the cloud. For example, if you had tail-in collisions, so beta and the momentum of the particle would point in the same direction, then cosine theta 1 would be equal to 1. And that means if the cloud would also move at the speed of light, then there would be no collision at all for particles coming in the same direction. So that makes sense. So the maximum collision rate would happen here actually for head-on collision. So cosine theta 1 equal to 1. So if we are now, and well, the collision rate, of course, depends also on the abundance of particles in our Milky Way. So this collision rate that I write down here is normalized such that if I'm integrating over the collision angle, this is normalized to 1. So I can now look for the, so this is the collision rate on particles entering the source. I can also look for the collision, or rather the exit rate. So on exit. So taking into account this isotopization of cosmic ray directions in the cloud, I can simply write the emission rate r theta 2 prime in the reference frame of the cloud as 1/2, 1/2, 1/2. So there's no preferred direction, so any direction is equally likely. And so if I'm integrating here over cosine theta 2 prime, there's only this factor 1/2 for normalization. Okay, so now we are looking for not only one cosmic ray particles, but we are looking for many of these particles. And so the net energy loss or gain will depend on the angular average of the different scattering and emission angles. So the angular average of theta 1 is now going to be given by this expression here. You integrate over cosine theta 1, and you have the collision rate, and you weigh cosine theta 1. If you now use the previous expression, you see that there's only one contribution, which is coming from the relative velocity. So this goes like minus beta over 3. And you can do the same now for the emission angle, theta 2 prime. And this is really simple. So this was just 1/2 cosine theta 2 prime. And this is simply given, this is equal to 0, not 1. This is equal to 0. So I can now use these effective scattering rates in this equation. So I replace here cosine theta 2 prime by the angular average in this factor here as well. This factor was equal to 0. This factor was equal to minus beta third. So putting everything together gives us now the following energy balance. So delta E over E1, our previous equation, becomes gamma squared 1 plus 0, 1 plus 1/3 beta squared minus 1. And beta here is assumed to be a velocity, a non-relativistic velocity. So I can assume that this is a small quantity relative to the speed of light. And the first order term is going to be 4/3 beta squared. And then you have terms that go like beta to the power 3. So from this original idea of Fermi, you can see two things. One thing is that on average, you actually gain energy. So repeated collisions of cosmic rays by this process has a positive sign. You accelerate particles in time, so that this is what we need. But the process itself has a dependence that goes like beta squared. And so this is the reason why Fermi's original mechanism of magnetic clouds scattering with cosmic rays is also called these days second order Fermi acceleration, because the delta E over E, the relative energy gain, is proportional to beta squared. And if beta is a very small quantity, non-relativistic, highly non-relativistic velocity, then this is a rather inefficient way of accelerating particles. Okay, any questions? So, okay, if there are no questions, I'll continue. So why is it that we still consider Fermi acceleration as one of the dominant acceleration candidates of cosmic rays in astrophysical environments? And the reason for that is the limitation that we just derived for the original Fermi mechanism was simply related to the geometry of the problem. So if we are kind of managed to change the geometry of the scattering process, where I now have preferred collisions head-on between the scattering particles, I can find an acceleration process that has a higher energy gain per collision. And this will lead to something which is called diffusive shock acceleration, where this is taking place. So for that, I will have a very short intermission. So in the following, we are going to talk about astrophysical shocks. And astrophysical shocks can happen in various places in our Milky Way and also in extragalactic sources. But of course, we want to connect back to our original discussion of supernova remnants. So let's consider core collapse supernova and the corresponding remnants which are formed by this event. So as you might know, stars are places where you can create heavy elements. So they are places of stellar nucleosynthesis. And the process which is at work here is, of course, nuclear fusion. And nuclear fusion is basically starting with lightweight elements, hydrogen, helium, and so on. And via the process of fusion, you can reach elements up to the iron group. So here, what I show here in this graph is the average binding energy per nucleon for nuclei. And you see that the binding energy is the largest in the region of iron. So that means if you start to fuse light elements in stars, then this is a process of energy gain. So you you increase the binding energy per nucleon, and this fusion process is a source of energy that fuels stars. Now, if you have a very heavy star, a star with a mass larger than about 8 solar masses, this fusion process will actually go all the way up to the iron group. And because the star is in hydrostatic equilibrium and iron is the heaviest element, the newly formed iron nuclei will be found in the center of the star. So over time, a star develops a shell-like structure. And between these shells, you have continued fusion of elements. And in the center of these stars, you have the fusion of very heavy elements, silicon to iron. And this is basically the end point of the fusion process. Now, this inner iron core of star is growing larger and larger. And the gravitational pressure in this iron core is going to become larger and larger because of the increased mass. But you do not have thermal energy generated by fusion in the iron core that can support the gravitational pressure. The only pressure that is available for the iron core to counterbalance the gravitational pressure is the electron degeneracy pressure, so the quantum mechanical effect. And but the electrodegeneracy pressure is basically constant, while the gravitational pressure is increasing with larger and larger masses. And there's a critical mass of the iron core, which is called the Chandrasekhar mass limit. So the Chandrasekhar mass limit mass is about 1.4 solar masses. Once the iron core has actually reached this mass, the electron degeneracy pressure is not going to be able to sustain the gravitational pressure. What's happening then is the iron core is going to contract, heating up the electron background. So you basically increase the Fermi energy of the electron background until the energy of the electrons reach such high energies that they can recombine with protons to form neutrons. So you basically eventually, due to the heating mechanism of the compressing iron core, you find you populate a very high energetic population of electrons, which then undergo inverse beta decay with protons forming neutrons and neutrinos. And this will reduce further electrons in this environment, and this will further reduce the electron degeneracy pressure. And you eventually end up with a runaway process where the inner iron core is collapsing. So this is the beginning of a supernova. And you can actually estimate the gravitational binding energy of this process. So you start with an iron core that has a mass of about 1.4 solar masses, the Chandrasekhar mass limit. And the gravitational potential, the binding energy that is released by the collapse of the iron core, is about 3/5 g Newton times the mass of the iron core squared. And then you just have the difference between 1 over the radius of the final object. I say in a moment what this is, minus 1 over r0, which is the initial radius of the iron core. So the final object is actually a proton-neutron star. And this infall of material will eventually stop when you reach nuclear densities. So very high densities, leading to a very compact object with a diameter of the order of 13 kilometer. So what you form is a proto-neutron star, PNS, and the radius of the star is going to be very compact, 13 kilometers. So because this is a very small quantity, you can basically neglect this additional correction 1 over r0 because the initial core of iron was much, much larger than 13 kilometers. So the gravitational binding energy is basically given by the size of the reduction of the iron core and the Chandrasekhar mass limit. So, and you can estimate the size of this gravitational release. And if you, for example, so the gravitational binding energy for 1.4 solar masses should be of the order of 3 times 10 to the power 53 ergs. So most of this gravitational energy is actually going into the emission of neutrinos. About 99% of this gravitational energy will be carried away by the electron neutrinos, which you produce by this neutronization process. Electrons combining to protons, forming, so you have electrons plus protons, forming neutrons and electron neutrinos, and they will carry 99% of the binding energy. So the remaining 1% of this gravitational binding energy, that can actually be can drive the outflow after the outer shell of the massive stars have bounced off the inner core and then reverse motion and produce the supernova remnant shock going outwards. So there are a lot of interesting details here that I'm omitting. For example, the neutrinos that you're emitting here are also very essential for the supernova explosion process itself. But we are not caring too much about these details, these important details for now. So what I'm going to assume here is that the kinetic energy of the remnant or the residual outer shells, which are bouncing off the iron core and going outward, will have a kinetic energy that is about 1% of the gravitational binding energy. And if you consider a mass of the star of the order of 8 solar masses, you can estimate that this leads to ejector masses, which are given by 2 times the kinetic energy divided by the mass of the ejector, which is roughly 1% of the speed of light, so c over 100. Yeah, so this is basically a very energetic outflow. It's still non-relativistic, but it's 1% of the speed of light. Now, what's going to happen later on with these ejector, that is basically a very complex process. You will start basically with a ballistic expansion into interstellar space. So at that point, the size of the radius of the supernova remnant will increase linearly in time. So R here is the size of the ejector. And this happens for a period up to 100 to 1000 years. And after that time, the ejector will have swept up enough material from the interstellar space, such that the mass that is swept up by the ejector is kinematically important. So basically, once the swept up mass from the interstellar medium reaches the mass of the ejector itself, then the ballistic expansion stops, and you will enter a new phase, and this new phase is called the Sedov-Taylor phase. So this is energy conserving adiabatic expansion of the ejector. And so this goes up to a time scale of the order of 10 to the power 5, so 100,000 years. And at this point, the velocity of the ejector slows down, and the radius scales like the time to the power 2/5. So this is a very famous solution derived by Sedov and Taylor, which can be derived from geometrical arguments considering what happens if you have an injection of very high energies into an environment that is filled with a gas, and giving these two quantities of gas and energy of the initial state allows you to derive this time scaling of the ejector. So this happens up to 100,000 years. Then the next phase is the so-called snow flow phase. So at this point, the ejector actually become radiative. They start to radiate away their energy. It's not energy conserving anymore, but you still conserve momentum. And the radius of the supernova remnant at this point will go like time to the power 1/4. And this goes on up to 1 to 10 mega years. And then after this time, you basically have a merger with the interstellar medium. So yeah, so this is basically in a very small nutshell what's going to happen in a supernova remnant explosion, supernova explosion and the following remnant. And what we are interested in is the Sedov-Taylor phase. So the Sedov-Taylor phase that is starting when the ejector have set up enough material from the interstellar medium, and when the velocity of the ejector is still very large. These conditions are ideal to form shocks. So you basically have discontinuities in the gas, basically the discontinuity of the ejector and the outer interstellar mass, which are becoming shocked. And these discontinuities are conditions where we also can look for particle cosmic ray scattering across shocks. And these particle scatterings across shocks will then again lead to an acceleration mechanism. Actually, let me at this point, so this is here one example of a supernova remnant. It's a fairly young supernova remnant, which was observed by a Danish astronomer, Tycho Brahe, 500 years ago or 400 years ago. And so this supernova remnant has now an age of about 400 years. And you see here a superposition of different electromagnetic emission. This supernova remnant right now is in its Sedov-Taylor phase, so this self-similar expansion, which is ideal for the acceleration of cosmic rays. So if I have, do I have any time left, Dario, or do I have to stop now?
You have still
maybe if I have
minutes, yes.
If I have 5 minutes left, then I can maybe nicely wrap up Fermi acceleration.
Okay.
So this was basically supposed to be a brief intermission of supernova remnants. So we can now go back to Fermi acceleration, and we consider now not the interaction of cosmic rays with clouds with randomly oriented velocity vectors, but now we consider cosmic ray scattering from one side of an astrophysical shock and the other side. So we are looking for the transition from one to the other side and back again. And this is basically the same picture that we had before, but we changed now the geometry. Now we have a planar shock front, which is indicated here as the blue line. And we can again look for the total energy gain per cycle, and the total energy gain per cycle has not changed. It's basically the same expression that we had before. Change to white. So delta E over E1 is still going to be gamma squared 1 plus beta cosine theta 2 prime 1 minus beta cosine theta 1 minus 1. So this is the exact same expression that we introduced earlier. But now we have different condition for the rate of collisions of particles as they enter the cloud and as they are leaving the cloud. And this will then give us different averages of the scattering angles. So the scattering rate from cosmic rays going from one to the other side of the shock, they are now looking the following way. So initially the collision rate will be equal to -2 cosine theta 1 for scattering angles which are larger than 90 degrees. But for cosmic rays streaming in the opposite direction, it will be 0. So there's no averaging over the angle lower than 90 degrees. We can also look for the emission from this right-hand side of the shock to the left-hand side. And this will look the same, except that now the collision will be 2 times cosine theta 2 prime for theta 2 prime less than 90 degrees. And for theta 2 prime larger than 90 degrees, this will be equal to 0. So now we are again, and this is the final point that I'm going to make today, we're looking for the average of these two quantities weighted by these different collision rates. And it turns out that the average of cosine θ1 is going to be minus 2/3, and the average of cosine θ2 prime is going to be 2/3. So we have now two different, completely different average conditions for the scattering angle. So if we are now putting back everything together, we see that delta E over E1 in this case becomes gamma squared 1 plus 2/3 beta, 1 plus 2/3 beta minus 1. And to leading order in beta, this is now 4/3 times beta plus higher order terms in beta squared. So you see, originally in Fermi's original idea, we had a beta square factor, but this beta square factor is now replaced by beta. And so this makes the efficient process, the acceleration process in shocks more efficient because the energy scaling, the relative energy scaling is proportional to beta and not beta square. And this is the reason why we are calling this diffusive shock acceleration also first order Fermi acceleration. And this is the last I'm going to say today. And then tomorrow we will continue with this supernova remnant shocks, and we will at that point also introduce radiative processes that lead to electromagnetic emission and the emission of neutrinos. Okay, thank you.
Any questions? Okay, apparently not. Okay.